Let me try to give you a little bit more intuition, something that the book doesn't dare go into. But I want to let you see what the Z transform actually looks like. So this is the Z transform for U of N. And yeah, let me go back and I'll just work out really fast what the Z transform is for U of N. We have this U of N. Actually, the simplest way to do it is we already derived it over here. For U of N, this A is just 1. So when you plug in 1 for this, it's going to be 1 over 1 minus Z to the negative 1. Z is greater than 1. So let me just write that down. That has a Z transform of this for this. Are there any values for which this thing blows up? Does it have any poles? Sure. When the denominator is equal to 0, it blows up. That's a pole. And so when it's Z negative 1 equals 1, it's a pole. So therefore, it's Z equals 1 is a pole. Let's see if there's any zeros. It's kind of hard to see if there's zeros because of the Z and the negative 1. I'm going to write it a different way. I'm going to multiply top and bottom by Z to get it in terms of positive powers. Everyone see what I did here? Just multiplied top and bottom by Z. And now it's even clearer that while we have Z equals 1 as a pole, we also have Z equals 0, which is a 0. The only way to see where your zeros and your poles are is to get them in the factored form in Z to the positive values. So if this is our x of Z, I'm going to graph the magnitude of x of Z, which will be the height over the complex plane of Z. So here it is. This is our transform of U of Z. And if we look straight down at the top, we've got our real part of Z, our imaginary part of Z. And now we're graphing the magnitude of the Z transform over that. And I've cut it off here manually at 5, but this, you can see this peak goes up to infinity, and it goes up to infinity at an input value of real part of 1, imaginary part of 0. So at that Z equals 1, just as promised, there's that pole. And then you can see that there's this 0. It pokes down here at 0 real part, and I'll rotate it around, and at 0 imaginary part. So it's got a 0 at the origin, and it's got a pole at 1. And that's what it looks like. This is what I want you to have in your mind. Then if we were to put a unit circle around the outside, around it, that is its DTFT. So this is the DTFT of U of N. And you can see that it's got a problem. It goes up to infinity over here. This is a difficult DTFT to evaluate. It goes up to infinity right at 0. But otherwise, it looks like this. And so if you were to unwrap this if you're to unwrap this thing that starts off here very, very high, and you'd expect the frequency content of a U of N to be really, really high, right? Because it doesn't change much. And then it quickly goes down to 0. And why doesn't it instantly go down to 0? It's because it has some high frequency content, because U of N switches from 0 for negative N to positive 1 for positive N. And so it has some of that high frequency energy. So there's its DTFT evaluated right around here. Its DTFT at pi would be right around here. So it would have a magnitude of about 1/2. And then it would grow all the way up to infinity back at 0 and at 2 pi. And let's just check that behavior of the Z transform against what we can see here in the DTFT pairs. For a U of N function, that's a step function, we see this complex magnitude component. But in particular, for omega equals 0, we see there's an impulse right here that causes the result to rise to infinity, just as we saw that pole forced the magnitude of the Z transform to go to infinity.